In this section, we want to see how to set up double integrals for non-rectangular regions. So many textbooks use this terminology, type 1 region, to refer to the fact that we've got a function of x on bottom and a function of x on top, but constants on the left and right. So we would have rectangles in our region whose bottom is a function of x and top is a function of y. So that's how we come up with the length of a rectangle. However, in the type 2 regions, like you see here, we would have rectangles running horizontally, where the right side is a function of y and the left side is a function of y. Notice that in this particular situation, if we had a rectangle going this direction, it would actually be going outside of our shaded region. So that's why it's not a type 1 region. You can't draw vertical rectangles in there and go from a function of x to a function of x. You can, however, draw horizontal rectangles in this region that go from function of y to function of y. Now here we have the gray shaded region that's bounded by the graphs of y equals square root of x and y equals x cubed. Now, when we talk about a type 1 region, that means that we should be able to put a vertical rectangle in this region and describe the function that's on top and the function that's on bottom of any such vertical rectangle within that region. And it's given in terms of x as y equals square root of x and y equals x cubed. So our type 1 region would go from the function x cubed to the function square root of x. Now here's that same region. If we were to draw horizontal rectangles, we would need to be able to describe each horizontal rectangle in terms of what is on the right and what is on the left. Well, as you can see, any rectangle we put horizontally in this shaded region is going to have its right side on the red graph, which is y equals x cubed, and its left side on the blue graph, which is y equals square root of x. Now the kicker is we've got to give those as x in terms of y. So we would have to take each of those and transpose or solve for the x to find out what the function of y is. Now in Calculus 1, we found the area of a region by taking a rectangle, placing it either horizontally or vertically, whichever was needed. In this case, vertical rectangles are needed because if you put horizontal rectangles on there, you wouldn't be going from one function to another every time. And we described the length and width of that rectangle. The length was top function minus bottom function. In this case, g of x minus f of x. And we integrated over -2 to 3. So that was the integral we set up in Calculus 1. Now let me just show you the integral, now that we know how to do such things. The integral of a 1 with respect to y from f of x to g of x would be a 1y with the g of x minus the f of x, which would come out to be the same thing that we had right here. And so we can write this area as the double integral. So if we were going to use double integrals to find the area of this shaded region, we would need to decide, is this a type 1 region or a type 2 region? Now, a type 1 region means that we would be able to draw vertical rectangles, and it would always go from one function to another. And as you can see, any vertical rectangle in this region would go from the blue graph to the red graph. However, any rectangle drawn horizontally does not go between the same two functions. You have some that go from the red to the blue, and you have some that go from the blue to the blue. So that is not a type 2 region. So setting up the integral for a type 1 region means that we do the order dy dx. First order of business is to decide what are the functions that y is going from and to. So we need this in terms of x. And so the bottom, which would be f of x equals x squared minus 4, would be our y for the bottom, and then our y for the top would be the x plus 2. Then we need the values of x on the left and on the right. And so that's the setup for the area of that shaded region in double integrals. Now we need to find the area bounded by these two functions, and it's the blue shaded region that you see here. We need to decide, is this a type 1 region or a type 2 region? So if we were to draw vertical rectangles, if this fits everywhere within this region, then it would be type 1. Well, it works fine here, but how about here? This does not go between the same two functions. One goes from the blue to the red, and the other goes red to red. So this is not a type 1 region. How about a type 2 region? If it's type 2 region, then horizontal rectangles have to go from the same function on the left to the same function on the right. That happens wherever we put our horizontal rectangle. It's always going from blue to red. So, having decided that it's a type 2 region, we will set up the integral with the order dx dy, and we need to decide for a rectangle, what would we use for the left and the right? Well, you can see the left side of this rectangle is on the blue graph, so we need x in terms of y. Well, it is in terms of y, so that would be the 2 cosine y. And then the right side would be the red graph, and again we already have it as a function of y. And then we need to decide about the y values. Here's the lowest y value. Here's the highest y value. Now, setting up an integral for things like this is best done with the help of some 3D graphing software. But we have a solid given as a function of x and y. That means z equals 2 minus x minus 2y. So that is a plane, and it's bounded by the coordinate axes. That means the xy plane, the xz plane, and the yz plane. So here is the graph of that region from Maple. And so I can see that I have a plane. Now, what I need to do is use the height of the plane and then the area in the XY projection. So here's the height. That just means the z value. So we've got the length times the area, which is what gives us volume. And so we need to set up the area. To set up the area, we will twist our graph so that we're looking up or down on the image in the XY plane. So here we're just looking up or down on the graph at the image in the XY plane. That is our region that we need to be integrating over. And so we need to describe that region now as either a type 1 or a type 2 region. So I've taken that line, found an equation for that line. Y is 1 minus x over 2, or x is 2 minus 2y. Both of those are the same equation, just written differently. One's a function of x, the other's a function of y. And if we do it as a type 1 region, we would imagine vertical rectangles, okay, dy first. So let's describe that rectangle as what's on the bottom and what's on the top. The bottom would be y equals 0, and the top would be y equals 1 minus x over 2. Then we need to decide what are the values of x on the left and the right. That would be the 0 and the 2. Now, as a type 2 region, we stick us some horizontal rectangle on there and describe that. The left side would be at x equals 0, and the right side would be x equals 2 minus 2 over y, the straight line. Then the y's would go from 0 to 1. So now to evaluate this integral by hand, if we don't have a calculator, we would begin on the inside, integrating with respect to x. We have the integral of 2, which would be 2x, the integral of x, which would be x squared over 2, and the integral of 2y would be 2y times x. So again, we can integrate this by hand. And then we need to plug in fundamental theorem of calculus, the 2 minus 2y for the x, and 0 for the x, and subtract. Then we need to integrate that with respect to y from 0 to 1. So in this one, we're trying to find the volume of the three-dimensional solid bounded by this paraboloid, which I've drawn off using my TI Inspire calculator, and the XY plane, which would be down here on the bottom. So the one that's bounded by that would be the solid dome-looking shape that we see there. Well, again, since we've got z in terms of x's and y's, we will use the idea that we need to use the z as the height and then multiply by the area. So we should have an integral where we've got the height times the area. We just need to describe the region. So like before, I would rotate the figure on my calculator so that I'm looking at the XY plane. So here's the image of that collapsed onto the XY plane. So I need to describe this region. And so we write z equals 0 for the XY plane. And so 4 minus x squared minus 2y squared equals 0 would give us x plus 2y squared equals 4. So that's the region that we're integrating over. We need to describe that in terms of x or y. I'm going to do both. And if it's a type 1 region, we have our dy followed by dx. We use a vertical rectangle. We decide what is on the bottom of this rectangle. Well, the bottom would be some y value. So there's the y value on bottom. That means the negative. And the y value on top, which would be the positive. Then we need to describe the x's. So we need the x value here and the x value here. Now again, you can kind of take a look at the equation. X squared plus 2y squared equals 4. And even if you can't tell from the picture, dividing through by 4, we've got x squared over 4 plus y squared over 2 equals 1. So this is a ellipse that goes from -2 to 2 in the x direction. So that's what we will use as our limits for dx. Now, as a type 2 region, we want to integrate first with respect to x. And again, we will use our rectangle, and we need the left side of the rectangle in terms of x's. And so we've got x equals this. We will use, since it's on the left, the negative one of those, and then the positive for the right. Then we need to describe what the y's are. And again, it's the same thing I just showed you. That would go from negative root 2 to positive root 2. Now, to evaluate one of these double integrals, this is pretty ominous looking. I'm going to type it on my TI-89. Now, taking a look at this integral, we need to describe the region in the xy plane described by this double integral. So we've got y's going from 0 to 4 minus x squared. So here is a graph of y equals 0, blue, y equals 4 minus x squared, red. Then we need to take a look at the x's, which go from 0 to 2. Well, x equals 0 is the y-axis. And so there's the region described in that double integral. Now here we're trying to reverse the order of integration. We have an integral given as dy dx. We want to rewrite it as dx dy. And so we need to first describe this region. We'll draw the graph off. So we got our y's going from 0 to square root of 4 minus x squared. Here's the graph. The red is y equals 0. The blue is y equals square root of 4 minus x squared. And this is what we use to set up the integral that we have. And notice here that the x's, according to the integral, are going from -2 to 2. So -2 to 2 on the x's means this is the region that we're talking about. When we reverse our order of integration, with the dx coming first, we still have to describe that very same region. Only this time we want to do it in terms of x's first. Alright, so we'll put us a horizontal rectangle on there, since we want to do this as a type 2 region, and describe the left and the right sides. Well, the left side is on the circle, y equals square root of 4 minus x squared, which we need to convert to x equals. So we'll square both sides, rearrange terms, square root. So the negative square root of 4 minus y squared is what's on the left of that rectangle, and the positive square root of 4 minus y squared is what's on the right side of the rectangle. Then we need to describe the y's, and again that's going from 0 to 2, since that's the radius of our circle.